Okay, today's class I'll tell you how to design the double lace column. So we'll go with the problem. Design a built-up member to carry an factored load of 1400 kilonewton and effective length is in the both the direction is 6.5 meters. The length is restrained and position but not in the direction at the both the ends. Provide double lacing system with bolted connection. Assume steel of grade Fe410 and bolt grade 4.6. Design the column with two channel placed toe to toe connections. Okay, so now in this they have given factored load of 1400 kilonewton. That means directly they have given the factored load. You don't have to factor it again. Then effective length is also directly given 6.5. But here they have given one of the condition is the column is restrained in position but not in the direction at both the ends. That means it is an hinge. Okay, anyhow they have given directly the effective length. If not, they will give you such type of conditions. You'll have to go with IS 800 and search which condition will suit and take the K value over there. Okay, and they have given us to design for bolted connection. For that they have given Fe value, grade of the plate and also grade of the bolt is given for us. We need to design for the column with the two channel placed toe to toe. Before we have done back to back connection, here it is toe to toe connections. Okay, first we'll write the given data. Given data carries marks. You will have to write the given data. Now here LE is nothing but they have given 6.5 meters effective length and PU is given 1400 kilonewtons. FU is given, FUB it is, that is now 400 Newton per mm square. What is FU? 410. Okay, this too we'll use it in the design of bolt. Okay, so now we'll go for the problem. Actually first we need to assume FCD value here. You can assume between 0.4, 0.5 and 0.6 Fy. 0.6 is 0.6 into 250, that will give you 150 Newton per mm square. I have assumed 0.6, you can also assume 0.4, 0.5. Okay, so as you already know what is the stress load divided by the area. We don't know the area but we have assumed the permissible stress over here, that is FCD value. We have already got here or assumed here. So whether we have assumed is correct or not, that we will check it at the later or the final stages here. But for the starting we'll have to find out the area first. So for that you need to take that stress is equal to load divided by area. So you know the stress, you will keep the area that side. So now load divided by the stress, that will give you what is the area required. Okay, so whatever the area you have got is for the two channel sections. You are connecting two channel sections, right? So here this whatever the area you have got, it is for the two channel sections. You can divide this by 2. So you need to search in the IS 800 IS steel table. In that you will get the area. Okay, so depending upon that you need to search the whichever the area you wanted. And I have taken here ISMC 350 at 42.1 kg per meter. Divide it by 2. Okay, whatever the area you get, nearer by area, slightly higher that area, you need to choose it. Here I have taken this height, breadth of the flange, thickness of the flange, thickness of the web, CYY, IXX, IYY, RYY and G. All these values you will get it in the steel table. You need to first see for the select the as a channel section. Depending upon that, all this value you need to write down. Clear? So now we'll go for the next. So as IS 800 says in the clause number 7.6.6.1, RYY you need to make it higher than the RXX or RZZ. So with that condition you will have to design the lacing. To bring out that condition, first we will have to take the slenderness ratio KL divided by R. As you already know, it is in the steel IS 800 they have specified 1.05 you need to multiply when you are designing for the lacing. I'll show you. When you see this clause, that is 7.6 clause, and it is in the page number 48. If you observe here, it is here, that is 7.6.1.5 will tell you the slenderness ratio KL divided by R. If you are designing for lacing, you need to multiply with the 1.05 times of KL divided by R. This is given in the code book itself. Okay, we have to find out the slenderness ratio KL by R. For the lacing, you need to multiply it with 1.05. So only I have multiplied with KL divided by R into 1.05. You already know KL, that is effective length, we have already taken or given in the problem, that is 6500 divided by R. There I told you, no, in the previous case we will have to design RYY that has to be greater than RZZ. Like that you need to design the lacing, because we leave the gap in between, right? Channel to channel we'll give the gap in between. So for that only we need to take RYY, that is whichever is maximum you need to take that. 136.5 that is in your steel table. So if you go for if you calculate this, you will get to the 50. Okay, so if you go for table number 9C, why it is 9C means it is a built up section, right? So if it is a built up section, you will have to take the clause number C. Buckling class will be C. So I have taken FCD as 183 Newton per mm square. Then load carrying capacity AE into FCD, effective area into FCD. So this is also in the code book. So now area into 2 I am multiplying, because we are taking two channel sections into 183, that is what we have achieved here. So that you will get 1964 kilonewtons, and always it is greater than 1400. That is like you need to design it like this only. Okay, whatever the load carrying capacity should be higher than the load applied. So this our conclusion is you can give so it is safe and you can provide to ISMC 350. Okay, we'll proceed. Okay, so now till now we have designed the columns here. This is ISMC 350, this is ISMC 350, Indian Standard Medium Channel Section. Now we'll design the lacing over here, the lacing on the both the sides. Okay, so I have taken this distance as S, that is the spacing between the channels. You can also take the distance this as an S, the gap between these two also S, and you can calculate it. I'll tell you what is the difference. You will end up with the same answer, but the difference is you will calculate only this distance, and then you will have to add up the width of the web. Okay, but we have taken totally as an S, you don't have to add up anything. You can do it in the both the methods are effective, or you will get the same answer, nothing changes in that. Okay, so now we'll calculate the spacing between the channels. So here we need to go for the geometric condition. We need to design everything, thickness of the lacing, and of width of the lacing, and also what is the length of the lacing, vertical height, horizontal spacing, everything you need to calculate. So first we need to calculate the spacing between these two. So I have taken, so first we need to calculate IXX and IYY. So whatever in the steel table you will get IXX and IYY, it is for the single channel sections, and this channel section separately, this channel section separately you will get. See here, you have the channel section like this, and it is that is connected toe to toe. It is like this. Okay, So here the different distance between these I have taken it as an S. You can also take the difference between distance between these two. So the whatever you will get it in your steel table, that is C section, X will be here, right, for this channel section, X axis, and here X axis will be here. Whatever you get IXX also, it will be with respect to XX. So for the whole of this you will get it in the same line because it is in the middle. So you don't have to calculate IXX separately. But what happens to IYY? So IYY will be somewhere here and here for this channel section. But combinedly IYY will come exactly somewhere at the middle like this. So you need to calculate separately IYY. Got it, no? So this is how you will calculate it. IXX you can take it directly. Okay, now we'll go with the problem now. So here I have taken IXX from the steel table. IXX, this is 2 times of IXX I have taken because we have taken 2 channel sections. That is equal to 2 into IXX, it is given in the code book itself. Okay, multiplying by 2. So IYY, as you have studied in your elements also, this will be the formula to calculate IYY plus AY bar square. So here I need to equate these two. Okay, so here IXX I have already know, IYY you need to calculate. Because I am taking 2 channel sections, you need to multiply it by 2. The small IYY will tell you what is the single angle Y. Okay, moment of inertia of single angle, that you will get it from the steel table. Plus area, again you will get the area from your steel table into the that is Y bar distance is from here to here, right, from here to here. So for to calculate that, S divided by 2 is nothing but totally this I have taken it as an S. S divided by 2 I'll get this distance, right. So that means this distance, S divided by 2. So now in this I need to calculate only these part, means I need to minus the CYY from the total S divided by 2, right. So S divided by 2, S I don't know, S divided by 2 I'll end up with these distance. So minus CYY you will get it from the steel table, that will give us what is Y bar distance. So you can calculate in the whole equation, S will be unknown, so you can calculate what is S, that is 316 mm. Now we got what is S. Now we will calculate what is the angle of inclination. So here you have you can take it between 40 to 70. It is from this specification is given in IS 800. Usually we will take it as 45 degrees. Next, horizontal spacing of lacing between the bolts is nothing but horizontal spacing between the bolts is nothing but that is center to center distance between the bolts. Okay, so in that the spacing is 316, right. 316, if I minus 60 and minus 60, I'll get the value, that is the horizontal distance. See, this is the channel section ISMC. This is just a single line diagram I am showing you. So this angle to the horizontal we have taken it as in 45 degrees. Got it? So now I want the horizontal distance. Horizontal distance is nothing but is totally I got just now we calculated it as 316 mm. Okay. Now this is 316. So now the gauge distance is equal to 60 mm, that is given in the code book itself. So angle section is some in this direction. Okay, so now from here to here the gauge distance is nothing but where you can place the bolt at what distance. So here you have if it is 60 over here and this is also 60. Okay, from here to here it is 60. From the center to the bolt to the next center of the bolt, that is what the horizontal distance is. That is we need to calculate. How do you calculate 316 minus 60 minus 60? Okay, that is the horizontal distance. So we got to know what is horizontal distance, that is 196 mm. 60 mm is the gauge distance that you will get it from the steel table. Next, the vertical distance or the vertical spacing or the vertical horizontal spacing, you need to take it as equal here because we are designing for double lacing. Now we'll go for the check for slenderness ratio. KL divided by R, as we have taken the distance over here, if it is safe or not, that you need to calculate it. So for that you have an equation KL divided by R. KL is nothing but effective length, will take this one only 196 because we are checking for this particular length. KL 196 divided by R is the R minimum 28.3, that you will get it as 6.93. That should be always lesser than 50. Again this 50 is mentioned in the code book. If you see in the clause number 7.6.5.1, it says it is about the spacing. It says whatever you get that spacing, it should not be greater than 50 or 0.7 times of the most unfavorable slenderness ratio. As we already know the length, we'll go with this only, that is 50. Okay, so you got it, no? So it is lesser than 50, so it is safe. Slenderness ratio, that means whatever the length we have given, 196 is safe. Next, the transverse shear, again we need to actually the lacing is not given to take up the loading, right? It is given to take up the shearing actions or to resist the shearing actions or the buckling. So we need to calculate the transverse shear here. Again, codal provision, you have 2.5% of the total load we need to design it or we need to take it for the transverse shear. See, it is here design of lacing. In this 25% of the axial force in the member shall be divided into the total in the parallel planes. That means when you are taking the VT transverse shear, you need to take the 2.5% of the axial force, and that axial force has to be multiplied with the all the lacing. Okay, how many number of lacing you are giving for a particular length, you need to divide equally to all the lacings. So now 2.5 divided by 100 is percentage, 2.5 percentage. So it is divided by 100 into the applied load is so much, is equal to 35 kilonewtons. Okay, so totally it should take 35 kilonewton. Now shear to be resisted by each lacing. Yes, how much? So that is 35 divided by 4. Why 4 is, see now here you have the lacing in this direction and here you have the lacing in this direction, right? So this is what we call it as in one length. Okay, this is L, vertical distance it is. Okay, so now this is the one vertical distance from here to here, and this will be the another one. So in this how many lacings you will get? See, this is the first one and 2, correct? And here this is 3 and this is 4. Got it? So how many members you have it in one vertical distance? 4 members. So in the double lacing, always it has to be divided by 4. In a single lacing, always it has to be divided by 2. Why single lacing do? Is nothing but here you have a channel section, only one side you will give the lacings, right? So in a vertical distance, how many lacing you have? 2, right? So you need to divide it by 2. In the double lacing it is 4, and the other direction also you will get it, right? From here to here, 1, 2, 3 and 4. Got it? So you need to divide it by 4. So now, only I have divided it by 4 now. So now next we will calculate the length of the lacing. Length of the lacing, you can see it here. This is the lacing. Consider this as a lacing. This will be the horizontal distance, and this will be the half of the vertical distance. Okay. So now here you need to find out the length. Length means, So here the sine rule we can use, opposite by hypotenuse. So 196 divided by the length, you will get what is the length of the lacing. We got it as 277.2. The theta is 45 degrees. Then we'll find out the thickness of the lacing. As we all know, this is the one more change in the compared to single. Here you need to take 1 divided by 60. For single, it is 1 divided by 40. It is specified in the code book. Thickness of the lacing. Here you have not lesser than 1/40th of the effective length for the single and 1/60th of the effective length for double lacing. So it has to be by 1/60. It should not be lesser than this. It can be higher than this. So it should not be lesser than 4.62. So I have taken it as a round off to 6 mm. So next we'll have to calculate the width of the lacing. Again 3 times of 16. Now what is 16? First we need to assume the diameter of the bar. So then after assuming, you need to multiply it by 3. Again it is given in the code book. It is in the clause number 7.6.2. Width of the lacing. Minimum width of the lacing bar shall be 3 times of the nominal diameter. For that only you need to assume the diameter first, then you need to multiply by 3 times of it, 3 into 16, so that you got it as 48 mm. So I have rounded it off to 50. So therefore we got the width also, we got the thickness also. You can conclude it as 50 ISF 6. 50 is the width, ISF is the Indian standard flat, that is the it is a plate, right? So we call it as in flats. Indian standard flats of 6 mm. You need to conclude it like this. Okay, next we'll calculate the area. 50 into 6, so that you will get 300 mm square. We have taken it correct or not, that you need to check for the slenderness ratio. So first we need to calculate R minimum. For that, square root of Ixx divided by area. I will be BD cube by 12 if it is a rectangle section. So 50 into 6 cube divided by 12 divided by area. So you will get R minimum as 1.73 mm. So KL by R is equal to whatever the KL you have got. So that is 277.2 into 0.7 you need to multiply. It is given in page number 50, clause number. 277.2 is the length, and in the clause number 7.6.6.3 here you have it has to be 0.7 times of, you need to multiply by 0.7 if you are designing for the double lacing. Got it? So this also is given in the code book. So divided by R minimum, just now we calculated it. Okay, so that we will get it as 112.03, and that is again lesser than 145. Again the same constant is given in your code book. So here in the clause number 7.6.6.3, the slenderness ratio KL by R, the lacing bar should not exceed 145. Okay, so this 145, that is the constant. So that should not exceed 145. So if it is exceeding, it is not safe. You need to go for the higher area. Okay, then we'll go for the connections, that is bolted connection, as you have to design for the bolted connection. The connection details, D you already we have assumed it as in 16 mm. D naught, that is the bolt hole diameter, is 16 plus 2, clearances 18 mm. I hope you all know this. We need to design for the bolt in the two condition, that is shear and bearing. First we'll check for the shear here, as it is a single shear. It is having only one C section and one of the lacing, correct? So it is only one shear plane you will get. So for that, NN I'll take it as 1, NS as 0. You can also take NS as 1 and NN as 0. You will get it as 28.97 kilonewtons, as you know this. So next we'll go for the bearing. You need to calculate what is kb. For kb you have 4 conditions. To calculate that 4 conditions, first you need to calculate E, edge distance and pitch distance. So you calculated edge distance and pitch distance. In the total of all the 4 conditions, whichever is least, that will be kb. So you substitute it here. One thing I need to specify here, thickness T. Taking the thickness T as 6 mm, because in the least of all the channel section thickness, and also lacing, you need to consider lacing also here. So 6 will be the least, that is lacing thickness is the least, so I have taken 6 here. So the bolt value will be the least of bearing and shear, so we got it as 28.97 kilonewtons. So what is the shear that has to be resisted for the each one is 8.75, right? We have already calculated this 8.75 in the previous one. So for that has to be divided by bolt value. Okay, so that has to be multiplied by so you got it as 1, that is 0.3, so that you got it as 1 number. Here you have, that is shear has to be resisted by each is 8.75, so that you need to take it here, divided by bolt value, so that you will get 1 number. Next we'll have to check for the strength of the lacing. KL by R also previously we have calculated it as 112.03. okay, here it is, we calculated this one, so 112.03, that only will take it for the next step. As 112 is in between 110 and 120, you need to interpolate. We need to go for table number 9C, as it is a built up section. So that take down the value. Fy you will take it as 250. Okay. So now whatever that 410 you got, that you need to write, and 120 you have got, you write it here. Got it? So interpolate between these two values, you will get it as 92.38 Newton per mm square. Okay, so then load carrying capacity, so that is the load FCD into area, right? So FCD is how much, just now we calculated it, into area is 50 into 6 of lacing, so you will get it as carrying capacity of lacing is 27.7 kilonewtons. So how much is load applied, force divided by sine theta, that you need to do it. So force, what is Vt for each lacing, for one single lacing is 8.75 into 10 raised to 3, it is in Newton, divided by sine theta, you will get it as 12.37 kilonewtons. Okay, this is what the force it is, shear force it is exerted, but its carrying capacity is 27.716, therefore it is safe. Carrying capacity is higher than the load applied, so it is safe. We can give this 50 ISF 60 at 45 degrees. Yeah, finally we'll go with the sketch. So you have the channel sections and both the sides. Whatever you are seeing is the flanges. Okay, it is in the side view. Then the lacing you need to give at 45 degrees, and it is a double lacing, crisscross. And we have already designed one bolt of 16 mm diameter. Give one bolts at the joints. Then we know the vertical distance, right, and horizontal distance is also 196. From here one bolt to the another bolt is 196, and vertical distance is also 196, and this will be ISMC 350 and 16 mm bolts. Okay, and this is about the design of double lacing system. Thank you.